Hi, everyone. Thanks for attending our presentation. I'm Amo Kamseti, and I'm here with Archib Kulkarni from the Ray team at Anyscale. And today we're going to going over two open source libraries, Ray and MLflow, talking about some of the work we've been doing recently to integrate the two of them and how we can use both of them to build an ML platform. So just to get started, this is obviously a huge team effort. It's not just us two. There's many people from the Ray team, as well as folks from the MLflow team at Databricks who helped with this work. So an overview of today's talk, we're first going to go over what are ML platforms and why they're important, then dive into these two libraries that I mentioned, Ray and MLflow, and then finally end with a demo of how what a sample ML platform built with MLflow and Ray could look like. So first, what are ML platforms? To first understand why we need an ML platform, you have to take a look at what a typical ML process looks like. While for hobbyists or independent researchers, ML development is mostly straightforward. And for production ML applications, this process is pretty complicated and involves many parts. Usually it starts off with some sort of business need and some time spent in initial research to find an ML method or technique which will be able to solve that problem. Then we go into an offline experimentation phase where we try out a bunch of different models, different techniques, make sure that those models perform well on our offline metrics. This involves a lot of training, which requires a lot of GPU and other computational resources, as well as hyperparameter tuning our models. Finally, when we determine that our models improve our metrics, we then go into productionization. And even then, if we don't see any improvement, we can end up going back to the beginning. So this process is complicated overall and is very time consuming. And just to put it in simpler terms, we can basically split up the ML process into two components. One is the execution, which involves the feature engineering, the actual training of our models, as well as tuning them, and finally serving them in both offline and an online setting. And in addition to the execution, we also have a management aspect, which involves tracking our data, our code, and configurations that we use in order to get reproducible results. And finally, being able to deploy our model in a variety of different environments. So how can we simplify this complicated process? Well, we can take another view of the process and see that there really is a split in responsibilities between what a data scientist or research scientist does versus what an engineer does. So data and research scientists want to focus on the ML aspects of this process. This involves using their expertise, doing the ML research, doing the initial data analysis, as well as the analysis of the predictions and model evaluations during the production stage. The work that the data and research scientists do is not generalizable across different applications. The models you use for recommender systems are different than the ones you use for fraud detection, for example, which is different than for reinforcement learning. On the other hand, we have the engineers. They handle a lot of the infrastructure, creating the data pipelines and training pipelines, handling the storage of your metadata, as well as your features and your data management. And they also are in charge of integrating with the CI system, for example, and taking your deployed model and making it available in a prediction service. The work that engineers do, unlike the work that the data and research scientists do, is generalizable across different applications. Regardless of which use case you're trying to tackle with machine learning, all of them have a need for the work that engineers do. And this actually leads to a natural abstraction. So this is where the ML platform abstraction comes in. With an ML platform, you can have a single set of tools that can be used by your data and research scientists across your entire company or organization, regardless of which application they're building or which use case they're tackling. The ML platform provides two main things. One of them is scalable infrastructure for your ML computation, and the other is productivity improvements. So a set of tools that make your data and research scientists more productive. So just to hammer this point home, we can take a look at some of the scale of ML platforms at some big tech companies. For example, LinkedIn has over 500 AI engineers building models, and they have over 50 engineers actually building the ML platform itself to assist these AI engineers. The ML work at LinkedIn actually constitutes more than 50% of their offline compute demand, and this is growing more than 2x a year. So clearly, ML platforms have become much more important in these companies. Many other companies like Uber, Airbnb, and Facebook are also investing heavily in ML platforms and have their own dedicated teams to build ML platforms from the ground up. So when building an ML platform, you can leverage a lot of different tools that already exist in the open source world. But going back to the original point of the two things you need are scalability and productivity. There's two libraries which you can use to solve these problems, and those are Ray and MLflow. With Ray and MLflow, you can solve these two problems of execution and management. Ray will solve the execution aspect by providing a framework for easy distributed and scalable for easily building distributed and scalable applications. And MLflow will help with the management of your experimentations.
So now I'm going to give you a little overview of Ray and some of its libraries. So first of all, what is Ray? It's a simple and general library for distributed computing. And so this will work across distributing work across multiple cores on a single machine, or even across hundreds of nodes. It's agnostic to the type of work. So here we'll be focusing on machine learning workloads, but it'll work for anything where you can parallelize and use distributed computation. And Ray also comes with an ecosystem of libraries for ML and for other use cases. So there's the native libraries built on top of Ray. That's, for example, RLlib, RayTune, and RayServe. And then there's also third-party libraries that run on Ray, and we've listed a few here. And finally, Ray comes with tools for launching clusters on any cloud provider. So it makes it really easy for you to actually spin up a bunch of machines and have Ray running on them. So there's three key ideas at play with Ray. The first is executing remote functions as tasks and instantiating remote classes as actors. So this is the task and actor paradigm from distributed computing. And it naturally maps onto functions and classes, which as a programmer, you're already familiar with. And the key thing here is this allows you to support both stateless and stateful computations. Another idea is asynchronous execution using futures. This is something that enables parallelism, and I'll give you a demo of this in a couple slides. And finally, there's a distributed immutable object store. And this allows for efficient communication where you can send arguments by reference. So let me give you a glimpse of the Ray API. So here we just have a couple of simple Python functions. One of them reads an array from a file, and another one adds two arrays. The primitive that Ray exposes is this @ray.remote decorator. And what this does is it takes an arbitrary Python function and designates it as a remote function. Remote functions can then be called with function name .remote, highlighted here, and this will return immediately with a future, which takes the form of an object ID that represents the result. So by calling this, many different functions can run at the same time. And you can also construct computation graphs using this API, and you can do it right in the Python code. Now, if you want to actually get the results, you'll call ray.get, and this will block until the tasks have finished executing and will retrieve the results. So this API enables the straightforward parallelization of a lot of Python applications, and you can find out more on the Ray documentation. So now I'll introduce another key Ray feature, actors, and these are essentially remote classes. As an example, here's a simple Python class with a method for incrementing a counter. You can add the remote decorator to convert it into an actor. Then when we instantiate the class, a new worker process is created somewhere in the cluster that hosts that actor, and each method on that actor will create tasks that are scheduled on that worker process. So in this example, these three tasks are executed sequentially on the actor, and there's no parallelism among these tasks, and they all share the mutable state of the actor. You can also easily schedule these tasks on GPUs by specifying resource requests, and this allows users to easily parallelize, for example, deep learning applications. So we use Ray to program what feels like an infinite laptop. With Ray, you have access to a rapidly expanding open ecosystem of scalable libraries, some of which we talked about earlier. And Ray functions as the universal compute substrate for all these applications. And of course, it runs on your favorite cloud. So now I'll pass it over to Amog, who's going to tell us a bit about RayTune.
Thanks, Archit. So as Arshia mentioned, there are many libraries which leverage Ray's task and actor paradigms to build other applications. And one of these is RayTune. RayTune is a scalable hyperparameter tuning library, which comes with many features. So first, RayTune comes with various search algorithms and schedulers from state-of-the-art ML research. So these include Bayesian optimization, hyperband, and population-based training. And in addition, RayTune is also compatible with many different ML frameworks. So regardless of whether you're training your models with TensorFlow, PyTorch, XGBoost, etc., it's still compatible with the RayTune's hyperparameter tuning capabilities. But the two main features that RayTune provides are focusing on simplifying execution. RayTune allows you to easily launch distributed multi-GPU tuning jobs. All you have to do is start a Ray cluster, connect to it, and then run your training function. And this will all run in parallel, regardless of whether you're parallelizing across the cores in your laptop or across hundreds of GPUs in a large cluster. RayTune also has automatic fault tolerance to save up to 3x in GPU costs, allowing you to use spot instances. And finally, RayTune also interoperates with other hyperparameter optimization libraries. You might already be tied into one of these other libraries, such as Optuna, HyperOpt, or SIGOpt. RayTune allows you to leverage their algorithmic advancements and benefits while still using Tune for distributed execution for its fault tolerance capabilities. So let's take a look into the API for RayTune. The first thing you need is to define a training function. So in this example, we're simply going to instantiate a convolutional network, train it for a certain number of steps. Now to add tune, what we need to do is add this tune.report line into this training function, which will report whatever metric you pass in that you're trying to optimize for, it'll report it back to tune. And finally, we take our training function and pass it into a tune.run call. And we can also specify any hyperparameters we want through a configuration argument. So in this case, we have a learning rate of 0.1. And you can also specify search space. So what this will do is you can run your training function. This will create 100 different samples or 100 different training runs. Each of them will have a different learning rate hyperparameter, which is sampled from this uniform search space from 0.001 to 0.1. And all of these different training runs are going to be run in parallel. With Tune, you can also easily leverage state-of-the-art schedulers and search algorithms. So for example, if you want to do asynchronous hyperband, you can do so with Tune. Or if you want to use population-based training, you can do that as well. And for some of these schedulers, you can also you also might have to use checkpointing. That's very simple to do with Tune through this checkpoint directory argument that gets passed to your training function.
All right, so thanks, Amog. I'm now going to talk a little bit about RayServe. So yeah, let's get into it. RayServe is, in a nutshell, a web framework built for machine learning model serving. So here's what it's like to serve your model on the web with RayServe. You'll just wrap your model in a class, and this class will have an init function. So you can initialize your model, and this step might take a while. Maybe you have to download a lot of data. And then when it's called, you can pass in a web request and then do any kind of pre-processing and post-processing you want before and after passing it to your model. So RayServe is high performance and flexible. So on the performance side, it's framework agnostic. It easily scales, and we'll see how easy it is in the demo later. And it supports batching and other features that are very useful for machine learning applications. But it's also flexible. You can query your deployments from HTTP and also from Python programmatically. And this allows you to easily integrate RayServe with other tools. What makes all this possible, of course, is that RayServe is built on top of Ray. So that means as a user of RayServe, there's no need for you to think about inter-process communication, failure management, scheduling, or any of these other things that make distributed computation hard. You can just tell RayServe to scale up your model. So here's what the RayServe API looks like. You can just serve any function or stateful class that you like, and RayServe will use multiple replicas to parallelize across cores and across nodes in your cluster. And the way you can query your deployment, well, there's two ways, like I mentioned. So from HTTP, you can just do it like that, or query it from Python using the Python API. And these will both query your model in the same way. Now let's talk about another piece of open source software that handles an important part of the ML lifecycle, and that's MLflow. So before saying what MLflow is, let's talk about some of the challenges of machine learning in production. Some of them are listed here. It's difficult to keep track of experiments, reproduce code, package and deploy models in a unified way, and there's no central store to manage models, including like their versions and stage transitions if some of them are still being developed or some of them are in production. So MLflow is one tool that handles all of these challenges, and it's library agnostic and language agnostic, so it'll work with your existing code. And it does this by 4 key functions: tracking projects, the model registry, and models. And we'll see how tracking and models work together with RayServe and RayTune in some of the integrations coming up in this presentation. But to give you an idea of tracking, MLflow allows you to log whatever parameters, metrics, or artifacts that you want. And here's some of the metadata associated with an MLflow model. And one important thing to notice here is the model can be serialized. That's what this pickled model is. And any MLflow model can be loaded as a Python function. And that's key to integrating it with RayServe. So now I'll hand it back to Amog to talk about some of the integrations.
Thanks, Archit. So we have 2 integrations between Ray and MLflow. The first one is with RayTune and MLflow tracking. So if you go back to if you recall from the previous example with RayTune, in order to use it with MLflow tracking, all you have to do is add this MLflow logger callback. What this will do is that whenever your metrics are being reported back to Tune, it'll also automatically get logged to MLflow under the MLflow experiments. There's also an alternative API you can use, which is the MLflow mix-in decorator. This allows you to have more fine-grained control of what's being logged to MLflow within your training function. So in this example, if we decorate our training function with MLflow mix-in, we can now specify MLflow to autolog and use MLflow's autologging capabilities, which will handle automatic logging for certain models such as XGBoost or PyTorch Lightning, which we will see later.
Thanks. And now I'll talk a little bit about the RayServe and MLflow integration. To get it set up, it's a pip package which you can install. And then to start running it, you'll start a Ray cluster and start a RayServe instance using these commands. And so here's what the command line interface looks like for this plugin. So there's many commands. One of them is create a deployment, sort of the most basic command. And you can see here we've specified -t RayServe. That means RayServe is the backend for this plugin. But you can use various other plugins as well, made by other communities, other companies. And here you can pass in the model URI. So any model that's stored in your registry, you can access it by a number of different URIs. They can be on S3, for example. And then finally, this -c num replicas equals 100. That's telling RayServe, that's a RayServe specific config parameter, to scale up the model to serve 100 replicas in parallel. So that'll really increase your throughput. And there's many other commands like deleting, updating, listing, deployments, and they all have corresponding things in a Python API. So from the command line or Python, you can use all of these commands. So here's the one for creating a deployment from Python. And integrating with RayServe is easy. This is because RayServe deployments can be called from Python. And this gives you a clear conceptual separation where RayServe handles the data plane, the processing, and MLflow handles the control plane, which is the metadata and configuration. So now we're going to give a brief demo of an example of building an ML platform using some of these integrations. So the MLflow RayTune integration and the MLflow RayServe integration.
Let's see how a data scientist or engineer would use an ML platform built with Ray and MLflow in order to train and tune a PyTorch model for MNIST classification, and then later on deploy that model into a web service. So this is going to be very bare bones pseudo ML platform. But for the sake of the demo, we'll show how we can leverage these integrations. So the first thing we need is a MLflow tracking server, which I've started here. So this is where all the team members are going to be logging their experiments to and being able to visualize their runs. Now that we have this tracking server, next thing we need to do is start our training. So I have a Jupyter notebook running locally, and what I'm actually going to do is connect to a remote Ray cluster. What this will allow us to do is still develop from the comfort of our laptop, but be able to leverage resources in the cloud through this Ray cluster that we're connected to. So as you can see, we have 4 GPUs available to us, even though this is running on my laptop. So now that we have GPUs, we can begin our training. I'm going to define this PyTorch Lightning very basic classifier here. And then we create our training function, very straightforward. Instantiate the classifier in our data set, create the PyTorch Lightning trainer, and call trainer.fit. What we want to make sure we do here is specify auto logging so that we can log our results to MLflow and then decorate this function with this MLflow mixin decorator. Once we define our training function, now we can do hyperparameter tuning. We want to tune learning rate hyperparameter over this search space. So we pass in our training function as well as our configuration to tune.run. And we want each training run to use one CPU and one GPU, and we want a total of 4 training runs. So once we create our tuning function, we can now perform our hyperparameter tuning, and we will see that these experiment results will show up on our MLflow tracking server. So this will take some time to train, but once this is finished, we will be able to see the results shown on our experiments tab here. And so the first thing we see is that the parameters are being logged, and soon, once this is finished, we will be able to see the metrics being logged as well. So now we have our 4 training runs logged to MLflow along with the models for each training run. So now that we have everything logged in MLflow, all we have to do is go through all of these runs which we've logged to our tracking server, find the one with the best validation accuracy, and register that model with MLflow model registry. So we just go through this. The model is now registered, and this is great. So now anyone can go and deploy this model, and we're going to hand it over to Archer to show how we can take this registered model and deploy it on a service using Ray Serve.
So here we're logged into a serving cluster. So we've seen this before, MLflow deployments create. -T, that's the serving backend. We're going to specify Ray Serve here, but you can use any other plugin like Redis AI, Torch Serve, or Algorithmia. And that's sort of what's nice about the MLflow deployments API and the plugin architecture. And we've specified the model URI that we had from earlier, and then we give this deployment a name, PTL deployment. So when we run this command, it's going to spin up one replica of this model on the Ray Serve instance. So here's the Ray dashboard, and you can see that one backend replica has been spun up. So one thing you might want to do is to update a model on the fly. So you can do that with this command. So here I've updated the existing deployment, but I've passed in a new model URI. And so when you run this command, Ray Serve will, without bringing the service down, swap out the new model in the backend. Another thing you might want to do is to take advantage of all the resources on your cluster, you might want to scale your model horizontally by making more replicas. So here's the command to do this. It's the same command, but we've passed in num replicas equals 10. So when we run this, it'll spin up 10 replicas that'll all be serving the model in parallel. So as soon as this command returns, we'll be able to go over to the dashboard and see that there are now 10 replicas serving in parallel. And finally, you can use the deployments API to run predictions. So for this one, we'll go to Python. And all these commands exist both in the Python and in the CLI interface. So it's as simple as this. You import the deployments API, and then you can run the prediction. Here we'll just run it on some random data, and we get some random output. And of course, you can query this over HTTP as well, but here we're just highlighting the integration with the deployments API. So this demo was kind of manual, right? We logged into the serving cluster and we ran all these commands, but you can also do this programmatically as part of a production pipeline. So for example, you could connect this to your continuous integration workflow. So upon each commit to your repo that updates a model, the CI could trigger a hook that connects to the serving cluster and runs a command to swap the new model in without bringing the service down. So we'd like to thank some of the people that made this possible. So in particular, thanks to Jules Damji, Sid Merching, and Paul Ogilvy for some of their help and guidance with MLflow. And of course, thanks to the ML platform demo team and the rest of the Ray team as well. And please join us at the Ray Summit. It's coming up in June. And it'll enable you to learn a lot more about Ray and a lot of the integrations with Ray and see how people are using Ray in the community. Thank you.